Morning.
Good morning, sir.
How are you?
Yes, sir. I'm good, sir. How about you?
I'm good, thank you very much. Are you preparing for your
Thank you, sir.
midterm or expecting?
Yes, sir. I'm preparing for midterm and for project.
So when will you present your project?
Soon, sir. I'm
No.
almost finished.
Okay. Makara, because you have to inform me earlier, so we have to schedule your presentation day. Okay, so at least like 2-3
Yes,
days,
sir.
if possible. By this Saturday, you should tell me, for example, let's say, Mr. Kasan, I will do my presentation next Tuesday at, let's say, 10 o'clock or 11 o'clock, so that I will just schedule and they will just prepare accordingly. Otherwise, if you
Yes,
just
sir.
come and if you just tell me that you want to do today, maybe I may not be available, or it may not be a suitable time for you, maybe for us. Okay, that's why we just pick a date, and maybe I will send you some options what actually days and times you can do. You have to choose one. Okay,
Okay, sir.
good. Okay, actually we were talking about matrices and matrix operations, matrix algebra, the inverse of a matrix, the LU factorization. In the previous videos, actually we talked about subspaces, basis, dimension, and rank. And actually also we did a lot of examples. And now we will talk about the last part, 3.7. For some reasons I will skip this because we don't have much time, so we have like at least 2 chapters that we have to cover. So just you have to study this 3.1 through 3.6. For now I'll just skip 3.7. So today we'll talk about linear transformation. It's just introduction, and also actually in chapter 6 and 7 we talk about this, but of course we'll not have time for that. So at least you'll get introduced with linear transformation. Okay, and we did a lot of examples with matrices, and if you have noticed that matrices can be used to transform vectors, acting as a type of function of the form. What is it? Here we have the form W is equal to T of X. And especially if you remember, for example, this linear a system of linear equation, A times X is equal to B. And what's going on here? Actually, we are just multiplying. This X is, let's say, if this A is M by N matrix, and this X must be X, not X, N by 1 vector or matrix, and B must be M by 1 vector. So that means that here, using this matrix, here we are talking actually picking a vector from n dimensional space. That is our X, right? And by just applying this, some kind of, what is it, transformation. Actually, this is our matrix. It's kind of transformation here is just taking this vector into this space, and this space is, what is it, n dimensional space. And how we are actually moving this, or just taking this vector from n dimensional space to another space, m dimensional space, by the use of these matrix. Now here, of course, we have a lot of transformations, because if you remember from calculus, for example, if you differentiate a function, right? For example, let's say if f of x is given, that is x squared, and if you differentiate this, and here we have 2x. And also differentiation, also a kind of transformation, because it's taking function into another function. And also integral, for example, also is a kind of transformation. But here, since actually here we are talking about linear algebra, so we will talk about a very important concept, which is linear transformation. That is a very powerful idea that will, actually, we will just see this repeatedly from here on. Anyway, so now let's just start with this example. Another example here. For example, let's say we are given one matrix here, A, and whose components are, let's say, 1, 0, and 2, 1, 0, 3, for example. And we are given another vector from two-dimensional space, let's say, whose components are, let's say, 2, 1, right? Now, what happens if we multiply this here? This A times V. A times V is 1, 0, 2, 1, 0, 3. And we should multiply this by 2, 1. And as you see here, this one is 3 by 2 matrix, 3 by 2. And this one is 2 by 1. And the resulting matrix will be, or vector will be 3 by 1. So here we will have something like this. Dot, dot, dot. So 2 times 1, 2, 0 times 1. So here it is 10. So here we have 4 plus 1, that is 5. And 0, 2, it is 3, right? So here, this shows that A transforms V into W. Let's say this one is W. Here, again, you're just picking one vector from two-dimensional space, and I want to take this element into this space. For example, R3 by some given transformation, right? And by just multiply this vector by some matrix A, right? It is just taking that element from this space to another space. Okay, that is what we're going to talk about here. Now we can describe this transformation more generally, actually. Now here, for example, instead of this, let's say V, not 2, 1, if I just put any vector from two-dimensional space, then this matrix takes to what vector? So here, not to 1, if we just pick any vector from here, let's say it is x, who's actually a vector x, or let's say it's vector v, whose components are, let's say, x and the y. So now, if you just multiply this by this matrix, ax, then here we will get this. So it is x times 1 plus y times 0, and here we have x, and here we have 2x plus y, so here we have 2x plus y, and the last one is x, and here we have 3y, right? Okay, actually this gives a formula that shows how A, the matrix A, transforms any vector from this one two-dimensional space, that is V. Any vector in R2, that is V, in R2, into the vector, this vector, right? Into the vector that is, let's say, W. So not X, I should write here V, because AV. Transform into the vector, this, which is an element in R3. That is our W. Okay. So actually, we denote this transformation by this transformation by TA, because the matrix is A, right? Using this A, we're transforming V into W. So now in a more, let's say, technical writing, I can just write it as, here we have transformation A, and here we have X, Y. Okay, I can just also put bracket because the vector that is, here we have x, 2x plus y, and 3y. Okay, this is how we're denoting this. It's a transformation, and using this matrix A, we are taking this vector whose components are x, y into this vector. This vector is from R2, and this vector lives in three-dimensional space. Okay, with this example in mind, we now consider some terminology. A transformation, actually this is what's going on here again. The transformation we are talking about this thing, right? Taking this vector into this. So it's like a function. It is a mapping, or simply we can just call this a function. T from Rn, in general, from Rn, this one is Rn to Rm, it is actually, what is it? It's just a rule that assigns to each vector v, in each vector v in Rn, a unique vector w. That is, what is w actually? That w is t of v, right? It's like a function, and here we have the domain, and here we have the range, and this one is x, right? Using some function here, and just actually it's in a sense y here. and that means y is here f of x. But here our function is the t. It's a matrix. Anyway, the domain of t is Rn, right? This Rn is the domain of t, and this Rm is the codomain of t. Anyway, it's just similar to function now. Let's just give a definition after actually getting some basic ideas. Now, what is a linear transformation? So a transformation T from Rn to Rm is called a linear transformation if it holds actually these two properties. Number one is, again, if you're just talking about this kind of space, right, that is Rn, and here we have space, here we have Rm, and here if you just pick two vectors, u and v, it's saying that first, if you just add them here, and transform this into Rm is the same as first just transform U into this space and the V into this Rm space, and after that add them together. They give us the same result. And the second one is if you just multiply the scalar, this V by C, and transform this, or first transform this V into this Rm, and after that multiply by C, again it gives the same result. That means that actually, that's why it's called actually linear transformation. That is the general definition of linearity. So immediately, let's just see one example. Determine if the transformation T, that's which is taking this vector from two-dimensional space into three-dimensional space, defined by this is a linear transformation. So here, to show that it's a linear transformation, we have to show that, right? These two properties hold. Number one is if you just pick any vector. Now here we are talking about R2, right? And XY. So if I just pick any vector here, let's say we have pick two vectors, let's say whose components are X1 and Y1. And the second vector, since it's living in two-dimensional space, is also components must be something like this, X2, Y2. So now I have to show that, we have to show that T of U plus V is equal to T of U plus T of V, right? And this is given, this is the description of this transformation is given by this equation. So now, from the left-hand side, T of U plus V. What is U plus V? That is, let me just write with a parenthesis, and I can just write it as here. What is U plus V? U plus V is X1 plus Y1, and here we have X2 plus Y2, right? So that is equal to, and here that X means just write the first component, right? The first component, that is the first component of this one is X1 plus Y1. And here, multiply the first component by X and multiply the second component by -1 and add them up. So that is, here we have 2 times X1 plus X2, not X2, sorry, that is Y1. That's the first component of the vector. So here we have Y1. And minus, multiply the second component by -1 and add it, right? So here we have X2 plus Y2. And the last one is, what's going on? And the last one is multiply the first component by 3 and the second component by 4 and add them up. So here we have 3 times X1 plus Y1 plus 4 times X2 plus Y2. Okay. So according to this transformation, if we just apply this to this X1 plus Y1, we will get this vector in R3. So now again, what is it? On the right-hand side, we have just a vector from three-dimensional space, right? And by just rearranging these things and using the simple algebra and simple algebraic manipulation, I can just write it here. We have X1 and 2 times X1 minus Y2, right? 3 times X1 plus 4 times Y2. I'm just going to separate them. And plus, also I can just write it as, let me just write here. I'm just going to write this as a sum of two vectors. Let me it's a bit big, so try smaller. Okay, so here we have the first component, right? So I can just write here x1 and plus. Okay, so this x1 plus y1, here we have x1, here we have y1. And here we have 2 times x1 minus y1. So here we have 2 times x1. Let me just write here. And minus y, the second component. The second component is, what is it? 2 times x1. Here we have 2 times y1, right? And here we have x1 and the minus x2. No, actually, okay. All right, here we have x1, y1, x2, y2. So we need to have here 2 times x1 minus y. What is y? Y is the second component. The second component is y1. Here we have, just a minute, x1 plus y1. Okay. So 2 times x1, 2 times the first component. Okay. I made a mistake here. This one x1, y1, and here x2, y2. So here we have x1 plus x2. So should you, okay, that's my mistake. So that is x1 plus x2, and this should be y1 plus y2. y1 plus y2. So it's the x1 plus x2, y1 plus y2. So here we will have x1 plus x2. Okay, sorry, let me just redo this. Okay, so here we have x, that's the first component. First component is x1 plus x2. 2 times first component, that is 2 times first component, x1 plus x2, minus second component, that is y1 plus y2. And here we have 3 times first component, 3 times x1 plus x2, and plus 4 times second component, that is y1 plus y2. Okay, here we have. Okay, so now I just try to write this as a sum of two vectors equals. So here we have the first one and plus here we have the second one. So here the sum of the two vectors, I can just write it as x1 plus x2. And this one is 2 times the first component minus the second component. That is 2 times x1 minus y1. And here we have 2 times x2, 2 times x2 minus y2. And here we have 3 times x1 and the plus 4y1. And here we have 3 times x2, because 3 times x2, 4 times y2, plus 4 times y2. Now, what is this? The first part is just the transformation of this vector, x1 and y1. And second one is the transformation of the second vector, that is x2 and y2, right? And that means that t of that thing is equal to t of the first vector plus t of the second vector. We have shown that t of u plus v equals t of u plus t of v, right? So the first property is shown that it holds. The second one is, how about if you multiply by 3? I need to show that t of c times u is equal to c times t of u. So that means t of, if you multiply u by c, let's say u is xy, so here we have cx and cy, right? And using this transformation, what we have here? Here we have c times x, right? And here we have the first component, and here we have 2 times cx, 2 times the first component, minus the second component. The second component is cy, and here we have 3 times the first component, that is 3 times cx plus 4 times cy. Okay. So you see here from each c is a common factor. We can just take this out, c, and what we have here? Here we have x, 2x minus y, and 3x plus 4y. And which is equal to c. What is it? It's just the transformation of that xy. So we can just write it here, t of x and y. Then the given transformation is a linear transformation. Actually, soon we will prove that actually every matrix multiplication is a linear transformation. But it's just a simple example to get some idea about this linearity. Okay. So now, after this example, we can just give this theorem. It says that if, let A be an m by n matrix, then the matrix transformation is given by this. From TA is taking the vector from Rn to Rm, defined by TA of x equals Ax for every x in Rn, is a linear transformation. So that A is a matrix, right? We have to show that it's a linear transformation. And how to show that, and also prove is very simple. That means that simply is this theorem is saying that this matrix, that A times x, if our transformation is this matrix by multiplying a vector by matrix, that matrix is taking vector into another vector, that means that there's always a linear transformation. So from here, let U and V, let's say, use different color here, let U and V be two vectors from n-dimensional space. And also let's say the C is any scalar, right? Then here we have, you just pick two vectors, the first property, U plus V, right? By this, right, by this equation, that means that this transformation is defined by this, that is the matrix A times X. What is our vector here? That is U plus V. So here we have U plus V. And just using the property of matrix, I can just distribute this A over U and over V. So here we have A times U plus A times V. And what is AU? Here this is AX, right? That is just the transformation of, what is it? U. AU. And how about this one? That is the transformation of V. Now we have shown that TA of U plus V equals TA of U plus TA of V. That is the first property. And how about the second one? We have to show that if you just multiply this vector by some scalar, and after that transform this, or if you just first transform and multiply by this scalar, it actually produces the same vector or gives the same vector. So here we have transformation of A, here we have C times U. U is a vector here. That is, again, by using this equation, I can just write it as A times vector. What is our vector here? C vector U. And again, by just using the property of matrices, I can just take the scalar out. So that is C times A times U. And what is AU? Just simply transformation of U. Okay, because I'm using scalar, that's why I need to use here bar to distinguish between C and U. So that means that now, if A is a matrix, then the matrix transformation is always a linear transformation. Okay, here we have one example. Let F be a transformation that maps a vector from two-dimensional space into two-dimensional space. That sends each point to its reflection in the x-axis. Show that F is a linear transformation. And it's saying that transformation that sends each point to its reflection in the x-axis. So that means that here, two-dimensional space, that is x and y, or x1, x2, doesn't matter. So if you just pick any point here, let's say whose coordinates are a and b, right? And this transformation is sending this point to its reflection above the x-axis. This is x-axis, right? That means that this one is, what is it? B, this point is A. So this transformation is just reflecting about the x-axis. So it's just sending this point to here. So this point, let me just say this one is P, point P, whose coordinates are A and B. Then it is reflection here, right? P prime, it will be A and minus B, right? So because x coordinate is not changing, only y coordinate is changing by only negative sign. So we have to show that it is a linear transformation. To show that, if I can show that it is just a matrix transformation, then it is done. Using the previous theorem, that means it is a linear transformation, right? So, okay, now here our transformation, right? If you're given any point here, A and B, right? And the result is, what is it? A and minus B. So the question is, can I just write this A minus B as a product of a matrix and what is it? A vector of AB. So we can do that. I can just write here, since it is 2, right? It must be 2 by 2 matrix. So if I just write here A and B, how can I get A here? So this should be 1, this should be 0. How can I get minus B here? This should be 0, this should be negative 1. So now if I just take this matrix as A, that is our vector, right? So let's say it is V. So this T of V is equal to A times V, which is a matrix transformation. Then actually it means that the given transformation is a linear transformation. What is it? It's just transforming every point in the coordinate system to its reflection about the x-axis. Okay, let me stop here. Let's have some break. After 10 minutes, I will continue.